Hey everybody, welcome to a brief introduction to Prolog. In this video I'll be going over the history of the Prolog language. I'll then discuss some of the features that make Prolog a great language, and we'll then dig a bit deeper into the standout features of Prolog, the things that really set Prolog apart from other languages. We'll then do a code demo where I'll be using Prolog to solve one of the exercises on the Prolog track on Exercism, followed by a listing of the resources that you can use to learn Prolog. I'm really excited about Prolog, so let's get started. Prolog was developed and implemented by Alain Colmeroer and Philippe Roussel in Marseille in 1972. So last year was Prolog's 50th anniversary. It's quite an old language. The name Prolog is an abbreviation of Programmation en Logique, which is French for programming in logic. Prolog is a dynamically typed language, but what's really interesting is the paradigm that Prolog supports, and that is logic-based programming. It is a completely different paradigm from functional programming and object-oriented programming, and it is very interesting in the way that you approach things. And we will get to the details later on. But for now, remember that Prolog supports the logic-based programming paradigm, which is very different from what you might know from other languages. Prolog's logic-based programming is based on horn clauses, which are a mathematical concept where there's only at most one true positive literal. But for now, just remember that horn clauses are Turing complete. So anything that you can compute, you can compute in Prolog. There are two major dialects of Prolog. One is ISO-Prolog, which was published and standardized in 1995. And there is Edinburgh Prolog. Of those dialects, there are many implementations, including SWI Prolog, which is what we use at the Prolog track on Exercism. There's Sixtus Prolog, there is GNU Prolog, and a more recent implementation is Scryer Prolog, which is actually implemented in Rust. So where would you use Prolog? Well, the classical use case is for artificial intelligence. IBM's Watson artificial intelligence system uses Prolog internally. So that was great because Watson actually participated in the game show Jeopardy, and it won against human opponents. And internally, Watson uses Prolog. So great work. You can also use Prolog well for natural language processing or for artificial language processing. There is a database called TerminusDB that allows you to use Prolog to efficiently query a very large knowledge base. And a final great example of where Prolog is used in real life is the Java virtual machine specification. And this specification contains type rules, and those type rules are defined and checked in Prolog. So if you look up the Java virtual machine type spec, you'll see Prolog rules all over the place. Let's go into the reasons why Prolog is a great language. First of all, it does things differently from other languages. In many languages, you are probably used to defining statements and they will be executed in order. So you have a firm grasp in how things are executed. In Prolog, you do things differently. You actually define your program as a set of relations. So these relations form a database, and you can then query that database to find answers, basically to compute things. But Prolog will handle that for you. There is a process called unification that we'll later see how that works, but it's almost like a fancy form of pattern matching. And this, paired with the relational model of Prolog, makes the very Prolog language incredibly powerful. It's absolutely perfect for any rule-based systems. Second great feature of Prolog is that it has very little syntax. There is only one core data type, it's called a term, and that has just a couple of subtypes: atoms, numbers, variables, and compound terms. It only has one structural element, which is called clauses, and clauses are entirely built from terms. And a clause can be either a fact, a thing that is true, or a rule, which is this is true if this holds. And that's it. That's the entire syntax. And this makes learning the language syntax very easy because there's just very little to learn. And it's also a very pleasant thing to work with because you will have a firm grasp of the syntax in no time. A third great feature of Prolog is that it is very declarative. I've already mentioned that Prolog requires you to think differently and that you use relations to define your program. And these relations are very declarative. So you define the relation, but you don't specify then when you query the database of relations how Prolog should find the answer. So you are working at a very high level. You don't bother with the nitty-gritty details of how things are processed, and you don't do for loops or whatever. You'll say to Prolog, these are the relations, this is my query, you handle the actual searching. And in many cases, this means less code. So it's better to maintain, it's usually easy to write. And it also feels very liberating to not to have to worry about all the implementation details. So Prolog is absolutely an incredibly declarative language, and that's a great thing. The last great feature that I'd like to mention is that it is designed to work very well for querying large search spaces. So if you have, I don't know, a huge search space where you need to find the optimal route for something, etc., Prolog has got you covered. Prolog has been designed to work well with very large data spaces, search spaces. So for example, it has different search strategies like depth first search or breadth first search. And it also supports things like automatic pruning. And that is a feature that makes Prolog more optimal, and that Prolog will automatically recognize, hey, this is a dead end. I don't need to search this bit of the search space. I can just safely ignore it. And that it greatly helps with finding a solution in a very large problem space. Let's discuss Prolog's standout features. First of all, Prolog is incredibly flexible. I mentioned before that Prolog uses relations, and these are defined as predicates, so things that are either true or false. And what Prolog, many of the built-in Prolog predicates have is that they work in multiple directions. And this is best illustrated via an example. So Prolog has an append predicate, and it takes 3 arguments. So the first argument is the first list, the second argument is the second list, and the third argument is the result of appending those 2 lists. So if you call this predicate with the first list being an empty list, the second list being the list with 3 and 4, and specify a placeholder for the third argument, Prolog will then infer that the placeholder value is the appended list, so that it's 3, 4 list. So that's like what you would expect in a regular language. But what you can also do is you can call the append predicate and use a placeholder for the first argument, so the first list, then do a concrete list for the second list and a concrete list for the appended list. And what that will do is that Prolog will try to see if there is a value that you can use for the first argument that will give you that appended list. So Prolog allows you to work in different directions. You're not just going from 2 lists to an appended list. You can also go from an appended list to the input list. And Prolog you can even use placeholders for the first and the second argument. And then Prolog will give you all the combinations of lists to get the appended list. So Prolog is incredibly flexible, and it works in 2 directions or even multiple directions. And this means that you can query and create data with the same syntax. And you can even use it's a predicate after all, you can use it to check whether or not 2 lists are, when appended, are a specific appended list. So you don't need a separate function for that. The predicate can be used to find data, to create data, and also to verify data. And this goes to show that Prolog is incredibly flexible. And some problems that are really hard in other languages become trivial in Prolog. It's like a cheat code. A second standout feature of Prolog are its definite clause grammars, DCGs. Definite clause grammars are a way to define rules for structured text. So they're like a parser combinator library. So if you have, I don't know, JSON as a structured format description, You could create rules for, hey, this is an integer, this is a string, this is an array, etc. And DCGs are a very neat and pleasant syntax to define those rules. And then Prolog will do much of the heavy lifting for you. You just define the rules, and then Prolog has the implementation to either to verify whether or not input data matches a certain format, to parse it, to unparse it, to generate data. So it is very, very flexible, as we just mentioned. And definite clause grammars are really, really powerful. And you can use them anywhere where you have structured data. It could be lists, it could be strings, it could be whatever your domain is. If you have a domain where you can parse something with a set of rules, DCGs are perfect for that. And then the final standout feature are constraint logic programming and CLP. And constraint logic program is you define relations, but you also define additional constraints. So for example, there is CLP-FD, which FD stands for finite domains. And for that, you can specify that a certain value must be in a range of values. So you could say, for example, that value X must be in the range 1, 2, 3. You can then also specify that value Y must be greater than X. And Prolog will then automatically infer that the domain of Y must be 2 or 3, because it must be greater than the first value. So it can never be 1. And Prolog, this is just a simple example, but you can do this for much more complex domains. And a lot of the problems that you see could actually be modeled as constraints. And with constraint logic programming in Prolog, you can define these in a very natural way, and it's also very, very fast. So it's an efficient way to model your program in terms of constraints. And it really is special how many programs you can actually define as in terms of constraints. So not just relations, but relations with constraints. Let's write some actual Prolog code. What I'll be doing is I'll be solving the queen attack exercise. And queen attack is about a chessboard with 2 queens positioned on it, and we have to determine whether those 2 queens can attack each other. So a queen can attack horizontally, vertically, or diagonally. So we see the chessboard here. There's a white queen at position 2, 3. So row 0, 1, 2, column 0, 1, 2, 3. And there's a black queen at 5, 6. And we have to determine whether or not these queens can attack. And in this case, that's true because they are on the same diagonal. For this exercise, I will be using Visual Studio Code, and I am using the VSC Prolog plugin. So let's look at our test file. The test file actually shows us that we need to do another thing. So we have a create predicate that takes in a row column pair, and that is true if it's a valid position on the board. Otherwise it is false. So 3, 3 is fine. Minus 2, 2 is not good, so we expect it to fail. And then once we have that, we can work on the attack predicate that takes in 2 pairs, and it's true if the pairs are positions of the queens that can attack each other. So those are the other tests. Let's look at our stop file. We have 2 predicates. One is create, and that takes in a single argument, position. The other is attack, and that takes 2 arguments, the white queen's position and the black queen's position. Currently, both these predicates are facts, and facts are things that are always true. And they are facts because we haven't added any clause. And we'll get to adding the actual clauses, but for now, these are facts. We can work with this code a bit by loading it into a REPL. So we'll open the terminal. I'm going to run swipl, SWI Prolog, and then I can load the file by using square bracket queen underscore attack.pl, and I'm going to do dot. And it says, well, we have some warnings about there being variables that we don't use, and that's true. But we can do create and then pass in 2, 3, do a dot. Dot is the thing that is the end of the term. So this is true. Basically anything is true here. So I can put in whatever. I can put in a. I can do whatever. It will always be true because these are facts, and the actual the rule will match regardless of the value. So it will always be true. Same goes for attack. So if we do 2, 2 and 2, 3, it will be fine. But also if we pass in invalid coordinates, it will be fine too. So we have a way to go. But you can see now that we have loaded the file and these relations are now in the database and we can query them as we want. So let's try and do something to actually implement the rules. Let's implement the create predicate. So we have to do something with the argument that is passed in. So this is now a fact and we want to convert this to a rule. So we can convert this to a rule by adding colon dash, and colon dash basically signifies to Prolog this is only ever true if this is true. So if we put in fail here, which is something that is not true. So if we then do make dot, reload the source code, then we'll do create to 4, it will be false. And regardless of what we pass in here, it will always be false. So let's add something more useful. So instead of fail, what we're going to do is we're going to need to extract the x and the y, or the row and the column. So row, comma, column is position. So this is not variable assignment. This is unification. And it's quite similar to deconstructing in other languages. So you're basically, what Prolog tries to see is there any way in which I can, this position can be deconstructed into a row and a column value. So it's like the structure has to be the same. We're not saying anything about the actual contents because these are variables. And it's important to note that if a term starts with a capital letter, it's a variable. So it's always a variable if it starts with a capital name. So that's why this has lowercase. So these are all variables. So this is fine. We can, there is such a unification possible because, well, we are passing it in that way. If we would have passed in as an integer, it would not work. We have to pass in as a pair. So then we need to do something with the row and the column. So the domain is it has to be greater or equal to 0 and less than or equal to 7. And this is a Boolean AND. So we're basically saying this must be true if this is true and the other things that I just mentioned are true. And in Prolog, you do that via the comma. So we're going to say comma, and then we can say row is greater or equal to 0. We're going to save this, and then let's just play with it a bit. So we're going to do make again, update the source. If we do create 2, 4, it should be fine because the row is greater or equal to 0. But if we do -1 here, it will be false. So we're making some progress here. So we can start continuing with this. So we're going to say row less than or equal to 7. But we get a syntax error. It says operator expected. You might be wondering, why is this not true? Well, this is because they found that this is very similar to, for example, this operator. So in Prolog, you actually have to write it this way. So it's a little quirk, but it's a good thing to remember. So less than or equal to is written as the reverse of what you're probably used to. So we can do the same for the column. And column 7. So we're going to do make. And then we no longer get a warning about unused variables here. So that's good, great. -1 is false. 1, 4 is true. 8, 4 is false. 7, 7 is true. So this seems to be working. There is one further refactoring that we can do. This whole deconstructing is also something that we can apply directly inside the argument definition. So we can do this, make again, and it should still all work. So we have implemented the first version of the create predicate. Then let's implement the attack predicate. We're going to do the same deconstruction trick. So row 1 call 1 and row 2 call 2, and then we're going to do colon dash. And the first rule that we implement is to check whether or not they're on the same row. So row 1 equals row 2. So let's go to the console, do make, then we're going to do attack 2, 3 and 2, 4. So different columns, same row, and it works. Let's try a different row, and it's false. So you might be thinking, hey, this is great, but we've actually done a thing that it might appear to be good, but it's actually not. So row 1 equals row 2 is doing unification, whereas what we want is we want to compare the values. So let me give you a little example. So if we do x is 4, what Prolog will do is unification, and that means that Prolog will try to find a value for x that makes the left and right side be equal. In this case, there's 1, there's 4. So that's fine. But if we it doesn't assign a value. So if we want to assign a value to x, we do x is 4. And then, for example, if we check x is equal to 2 times 2, we get false. So the reason for that is because this is a variable and this is a compound term, and they are different. They don't unify. So if we want to compare the value of x to the right side value, we're going to do equals colon equals. And this is right because it's now actually comparing the values. So what we need to do is we need to do equals colon equals. So equals colon equals. We can do the same thing for the row, for the column, and we have to do something a bit differently from what we did before, because we did and with the comma. Now we need to do or, and with or you use a semicolon. So we're going to say call 1 and call 2. So we're going to do make, and this is different rows and different columns, so it's failing. Different rows, same column, it's working again. So use the semicolon for the or. Then the final condition is the diagonal, and for the diagonal we can use a little trick. So we're going to do the absolute value of row 1 minus row 2 must be equal to the absolute value of call 1 minus call 2. If you're unsure how this works, just draw it out. We'll do make. We're going to do different columns, different rows, but same diagonal, true, and different, not on the diagonal, it's false. So this is our first working version of the attack predicate. We should actually have a working implementation now. So I have a second command open here. I'm going to run all the tests using this bit of syntax, and it says all tests passed. We could also have done this differently. We can also load the queen attack test.pl file, tests. Am I wrong in the naming? Queen attack, oh, PLT, my bad. So we're going to load this file, and then we're going to say run test, and we can run all the tests in the console too. So we have all the tests passing, and that's fine. This error we're going to ignore for now, and we'll come back to that in a second. Let's implement a little refactoring. So the create predicate we can simplify a little bit, because these are range checks, and there is a built-in predicate to help us with that. So let's open the console, and we're gonna try, there's a between. So lower bound, upper bound, and then the value. So this is true. So this is false because the value is outside of the bound. And we can use that in our code. So let's convert this to between. And we're going to say 0, 7 row, and I'm going to do the same thing for the column. I'm going to replace all this. I'm going to do make, and we're going to run the test again, and it still all passes. Just to show you how that things in Prolog can work in different directions, we can also do between 0, 7, x. So we're going to do a placeholder value for the third argument. And if we run this, Prolog will say, hey, the value 0 is valid. And I'm going to do, if I press the semicolon, I will get the next value. So Prolog will iteratively try out enlisting all the possible values. So you could even use the between predicate to find all the values in a range. So it's not just a check, you can also use it to generate data. We can also refactor the attack predicate a bit. So currently we have we have 3 different rules, and they are ORs. What we can also do is we can split up the single predicate into multiple predicates. So what we're going to do is we're going to basically copy this bit. So we're going to do attack, and then we're going to do this, and we're going to do a dot here. We're going to remove this. We're going to do the same thing for the column-based rule, and then we're going to get rid of that too. So I'm going to move them all next to each other. So we now have extracted the different clauses into separate rules. So instead of having 1 rule, we now have 3 rules, but it's still the same thing, and Prolog will work fine. So if we do run test dot, all the tests are still passing. The only thing that we get is just the same error as before, and we also get singleton variables. So we don't use call 1 and call 2 here, so we're going to do underscores. We're going to do the same thing here. So run make again, so we get rid of some of the mistakes. If we run the test, we still get the choice point thing. So what is that? Well, it's actually due to the fact that Prolog tries to find all possible solutions. So, and Prolog will do backtracking. So if we do x row is 2, 3, and we're going to do the second one is 2, 4. And we're going to do a dot, then it will say, hey, it's true. And this is the first predicate that's matching. And if I do a comma, Prolog will try and continue to find any other matching predicates, matching rules. And that's because we haven't told Prolog to stop searching, basically. So by default, Prolog will start to find this, and then it will find that, oh no, these other 2 don't match. But in our domain, we already know that once we have this match, we don't need to search anymore, because we don't need the actual other values. We're just fine. And in Prolog, we can do that with a cut. So we're going to do comma, and then we're going to specify an exclamation mark. And the exclamation mark will inform Prolog that Prolog can stop doing any backtracking. This is the end result. There will never be any use for doing backtracking or looking at other predicates. So we're going to run this again. I'm going to run the test, and this time we got rid of our choice point warning. So now we have a proper Prolog solution that doesn't do unnecessary backtracking. As one final refactoring, we can convert this to a different type of solution. We're now using regular relations, but we can also use CLP-FD. And CLP is constrained logic programming. FD stands for finite domain, so bounded domains. And to use that, we first need to do this. So I'm going to have to use a module. And what this will allow us to do is to define our problem in terms of constraints. So this between 0.7 row is a constraint. So we can write this in a different way. We're going to say row in 0.7 and call in 0.7. So this should be the same thing, but it's using a different implementation under the hood. So it still all passes. So now we have used CLP-FD. So we're going to say the value row is in this domain. And we can also do a little trick. We're going to do row and col. We'll put them in a list, and we're going to say every value in the list must be in the domain. So we're going to do ints. So this is the same thing. Whether or not you like this better, it's up for grabs. But this is all neat. But I'm gonna refactor back to just the original version because I think it's a little bit clearer. So that's the first thing. Then we need to look at the this little bit. So the equals colon equals. So how do you define that in CLP-FD? Well, you do hashtag equals. We're going to do hashtag equals here too. So we're going to do hashtag equals here too. So make, run the test, and it all passes. And this might look very similar, but it is using CLP-FD, so it is different. But it also has different options. So we can do x is for let me see, 4 is x plus 2. That doesn't work. So if we do 4 is x plus 2, it doesn't work either. So if we're going to do 4 equals colon equals, it doesn't work either. But if we do hashtag equals, then suddenly Prolog does understand it. We don't need to go into the technical details what arguments are not sufficiently instantiated means, but it essentially boils down to that Prolog can't find a solution. Whereas with the constraint logic program, Prolog does understand this. So hashtag equals is more powerful in that regard, in that it can work with these variables inside complex expressions. So now we have a working version that uses CLP-FD. Let's go over the resources that you can use to learn Prolog. Of course, you can learn Prolog on Exercism. The Prolog track has 40 exercises that are dealing with strings or integers or a lot of different things, but there are also some Prolog specific ones. So one of the exercises that is very famous in Prolog is the zebra puzzle. It's also known as Einstein's riddle. So you have a list of rules. These are all true, but you have limited knowledge. But with these rules, you should be able to figure out the solution to this exercise. So this is a great way to show the power of Prolog, where Prolog can figure things out for you just based on a couple of rules. There are more exercises. This is one is Prolog specific, so it's floored, and you get a similar thing where there are 5 floors, etc. So these are basically integer constraints, so that gives you a hint of how you can solve this. And there are 2 more. So besides floored, there's also garden party and Cheryl's birthday. So those 4 exercises are all great to get a feel for Prolog and its logic-based programming paradigm. But we have many more too. So a lot of the exercises, if you've solved them in another language, it's very interesting to see how you would solve them in Prolog and whether or not you can write them in a way that is very different from what you might already know. Besides the Prolog track, you can learn Prolog via the Getting Started guide on the official Prolog website. So there's a lot of stuff here on how to start up a REPL, how that works, how to load files, etc. So a very good Getting Started section. There's also an examples Prolog section. So we have a lot of examples here. So for example, I can click on Sudoku, and you'll see this is a Sudoku solver in just, well, what is it? Maybe 12 lines or so. And then I can put here some code, run it. Yeah, that will do it. And you'll get the solution of the Sudoku puzzle. So this was the problem, the solution. And this is the code to solve it. It's a classic example of the power of Prolog. And I think this showcases it very well. There are a lot of links to learning resources on the official Prolog website. So from different Prolog tutorials to specific tutorials on aspects of Prolog, like definite clause grammars, etc. Really useful. And there's Learn Prolog Now, and that contains an introduction, a step-by-step introduction into the language of Prolog. So starting with the basics, what are facts, what are rules, what are clauses, queries, etc. And then slowly building up more information. So at the end, you'll be a very powerful Prolog user. There is the power of Prolog, which I really, really like. It is a large series, so there are many different concepts it explains. And what makes this one really great is that it also has accompanying videos. So for a lot of these things, you can watch a video online, and it will go into not only the basics, but also some more advanced stuff like the definite clause grammars, etc. So a lot of very cool stuff here. The Prolog site is also some courses that you can use to learn Prolog, paired with some exercises. So for example, if you click on arithmetic, you'll see here you get a set of questions, and then there is a solution that you can find, so you can check whether or not what you came up with it was right. There is Learn X and Y minutes, where X is Prolog in this case. So these are there for many languages, and there's also one for Prolog, where you get introduced to the syntax of the language and the semantics very gradually, but always with code examples and comments that explain you how it works. And then finally, if you like to read books, one very nice book that also covers a bit of Prolog is 7 Languages in 7 Weeks. And I mentioned this because I have the book here, and I'm doing a giveaway. So if you complete and publish 5 Prolog exercises this month, give me a shout out in the comments, put in your Exercism username, and you'll enter the giveaway, and I'll randomly select a winner and send the book to you. So let me know if you are interested in that. And with that, we've reached the end of this video. I hope this introduction to Prolog has been useful to you, and that you now have an idea of how unique Prolog is as a language, and that you're now maybe even keen on trying out some Prolog. If you do, leave me a comment, and I'll be very interested in hearing your thoughts on how Prolog works for you and whether or not you like it. So see you next time. Bye.